in the background. So they can recognize your voice for the security stuff. Yeah, actually I know it because one time I called Fidelity. Oh, they asked me to enroll my voice. I actually did that for fun. Recently, some major banks, for example, the Chase Bank, Citibank, Fidelity, they already start to use the voice biometric system in their call center. Maybe it's a good news for the customers, it's more convenient, but because everyone knows recently the deep learning developed very fast, so the AI now can create the voice using a few minutes of your recordings, can create a very realistic voices. There are a lot of startups doing this kind of voice cloning toolkit or systems. There are also some open source toolkit that can do this task. For example, the toolkit Zhizheng is working on the system ESPnet. They can also do the synthesis of voice cloning, this kind of work. So the voice cloning toolkit is generally available. So the question becomes, if we can clone your voice, so is the voice biometric system still safe to use? A few years ago, we did a study. We use at that time it's still not the deep learning models. Is some the classic HMM decision tree TTS system. When we use that system to clone the target speaker's voice using 20 to 30 minutes speech, when we use this voice to spoof the speaker verification system, we found there is a very high chance to spoof the speaker verification system. I believe many of you already know speaker verification. So in this diagram, is the green line is the score for the real speech. The blue line is the imposter score distribution. The ideal case, the genuine score and the imposter score distributions, they separate very well. But when we use the voice cloning to spoof the speaker verification system, actually it can move the imposter score to closer to the genuine score. So it's not a good news. It means the spoofing can present a threat to voice biometric systems. So this is the one concern. Actually, there is another concern for the disinformation. Maybe you are not aware of it. Disinformation means someone manipulate the information. Maybe only part of the information, or they create a fake news, this kind of information. So earlier this month, there are 2 deepfake videos have gone viral. So a lot of you, if you check the YouTube video, how many people view it, there are millions of views. So it means this is a threat to the community, especially recently there is an election. So it can deliver the misinformation to the general community. So let me play one video. In this video, maybe for the first 5 seconds, you can close your eyes to listen to the audio, just to see, to feel how natural of the fake audio. After maybe 5 seconds, you can watch the video at the same time listen to the audio. You can see which one is harder for you to decide is a natural or a fake. Let's start it. It's a 30-second video.
Democracy is a fragile thing, more fragile than you want to believe. If the election fails, there is no democracy. I don't have to do anything. You're doing it to yourselves. People are divided. Your voting districts are manipulated. Voting locations are closing, so millions can't vote. It's not hard for democracy to collapse. All you have to do is nothing.
Okay, this is a fake video. Actually, the first time I watched it, because I know this gentleman, but I never watched his presentations or watched his speech. The first maybe 2 or 3 seconds, I thought, it's so real. It's a real speech. But at the end, I know, it's a fake one. So I will play another one. This one is purely the audio deepfake with some images, with some photos. You can listen to it. I think it's for the ordinary people, maybe it's so real. But for you guys as an expert, I think you can detect it's easy to know it's a fake one.
The military force of the United States has 3 distinct divisions: the land losers, the sea suckers, and the just plain stupid. I would have been proud to serve in any of these divisions had it not been for 2 medical disabilities, bone spurs on my feet, and the complete lack of a spine. So unless they get captured, or even worse, become transgender, our servicemen and women will always be some of my favorite people with guns.
So for this fake audio, actually they mixed with some background music, because after we mix with some background music, it's much harder for you to detect is a real speech or a fake one. From what we can see, that is audio deepfake actually is a prisoner threat to security. Voice biometric is a main one. There is another problem with cyber security. For example, is a prisoner threat to our community. For example, the election, it can deliver many misinformations. So today, I will first talk about what kind of technologies are available to create the fake audios. After that, I will give a brief introduction of the two technology which use deep learning to generate speech, to generate audio. We will discuss the state of the art and discuss what kind of artifacts it can produce. These artifacts can help us to design the detectors. At the end, we will review what the community has done to detect the audio deepfakes. After each submodule or each section, I will leave some time to answer questions. Generally, there are 4 types of techniques to produce fake audios. The first one is impersonation. Impersonation is very straightforward. For example, I can try to mimic the style Shinji is talking about, try to mimic Shinji talking. Another one is we can do the replay. For example, when Shinji is talking, I can pre-record some of his voice and then do some other playback in other scenario. The third one is voice cloning. We can also call it text-to-speech synthesis. We take maybe a few minutes training data from you and to train a model to generate your voice. The last one is voice conversion. For example, train a model to convert my voice to sound like Shinji. So what is impersonation? Impersonation, as the word says, is mimicking a target speaker's voice without any computer-aided technologies. I will play a very short video, 20 seconds. You can get the idea what is impersonation.
Gentlemen and lady, start your impersonation.
Silent extra orange.
11 Trump imitators competed at Los Angeles Comedy Club, The Laugh Factory.
And I want to assure everyone here, I have no Russian ties. They're all made in China.
Riffing on the president's words.
The media's been so unfair, believe me.
Aping his gestures. Clapping, pointing, pouting, even breathing like him.
But I mean, you know.
Among the judges.
Look at this.
Former SNL.
Okay, yeah, I think you already get some idea what is impersonation. Yeah, if you want to watch the entire video, you can search them on YouTube. So here is an example of speech impersonation from the speech representation point of view. The first column is a spectrogram of a speech. The second column is format tracks. So in the first row is the impersonator's natural speech. The second row is the impersonated speech. So the impersonator is trying to mimic the target speaker. The last row is a feature representation of the target speech. You can see when the impersonator want to mimic the target speaker, they can change their speech property to closer to the target speech. But from the spectrogram, you can see there is still a gap between the impersonated speech and the target speech. So we can say actually impersonation is not that effective when we want to mimic the target speaker, because not everyone has the talent. Because, for example, for me, it's very hard to mimic. I don't have the skill to mimic another speaker. I cannot mimic Zhizheng's voice. Playback is very easy. It's just play a pre-recorded speech collected from a target speaker. I believe everyone has a smartphone. So in the smartphone, you have a recorder. You can easily do the recording anywhere, anytime. So let me show you a photo here. The left is a genuine speech, the spectrogram. The right is the playback speech. Actually, from the feature representation, they are almost the same. Let me play you two audios. First is the genuine speech. Second is the playback. You can see from the listening perception, they are also the same. The first genuine speech.
No return address whatsoever.
Playback.
No return address whatsoever.
Yeah, there is slightly some background noise reverberation. Yeah. Okay, here is a comparison for the accessibility and the effectiveness of the different techniques. For the impersonation, as we have seen, the accessibility is low. In theory, everyone can do the impersonation, but not only a few people have the talent to mimic a target speaker. For the effectiveness, so to spoof a voice biometric system, the effectiveness is very low. So the ability to create the disinformation is also low. It depends on how the people can mimic the specific target. For the playback, because everyone has a device, so the accessibility is very high. The effectiveness to spoof voice biometric system is low to high, depends on what kind of speaker verification system you have. Maybe for the text independent is easier. For the text dependent is much harder. For the disinformation, because replay is not changing the content, so it's not applicable to disinformation. For the text-to-speech and voice conversion, because nowadays there are a lot of toolkit and a lot of startup working on the systems, so the accessibility is very high. The effectiveness is also very high from the literature. So today we will focus on the text-to-speech and voice conversion spoofing. Yeah. Do you have any questions so far? If no, we will move on. Let's first talk about the text-to-speech synthesis. Text-to-speech synthesis, from the name, you can see, is to given a sequence of text. We want to convert it to the audio signal. So the end-to-end problem to solve is how can we map the letter or character sequence to a sequence of the continuous numbers, which is audio. In practice, we divide the end-to-end problem into 3 stages. The first stage is to do the text processing. Text processing is to extract some linguistic features, some features which can be used for the regression. Regression is to convert the linguistic features to some audio representation, for example, mere spectrogram. So the waveform generator is to reconstruct the audio. So here is how the text processing works. For the text processing, it takes a sequence of text, then do the tokenization, and do the normalization. Normalization means, for example, we have the a digit 5, we can convert 5 to verbalize it. The part of speech is part of speech tag is to get the part of speech, and also predict the pronunciation of that letter, and predict the intonation feature, prosodic features. So here is an example. For example, we have the hello world, 2 words. We can use the text processing to extract features. We can extract the part of speech. We can get the how many syllables, and we can also get the phones for each word. The regression is to take the linguistic feature as input, use some machine learning models to get the acoustic features. Linguistic features is discrete features. The acoustic feature is some continuous features. So we can use some machine learning models to do that. For example, the classic method before the deep learning, we use a regression tree to do the mapping and use the HMM to learn the state of the speech. You can also use the feed-forward network to do the frame by frame or state by state mapping. We can also use some recurrent network to take account of the temporal information, because speech is the temporal information is very important. The most recent method is to use some encoder-decoder. As we can see, the linguistic features and the acoustic features, they are having different lengths. So we want to use the encoder-decoder to do the sequence-to-sequence mapping. Yeah, as we talked, encoder-decoder is to do a sequence-to-sequence regression. So it will take the numerical values of this kind of linguistic features as input to get some hidden state, then use a decoder, of course, with some attention mechanisms to predict the corresponding acoustic features. This is the idea of the sequence-to-sequence regression. If you are interested, you can read some papers on the Talktron. That is maybe the first successful system to do the sequence-to-sequence mapping. For the waveform generator, in the last few years, actually there are a lot of new work comes out to in the waveform generator. In the 1990s, the main method is doing unit selection. Unit selection is we cut the audio recording into small pieces, and then we concatenate them together, depending on the context. In the 2000s, in the early 2000s, there becomes a parametric system. So they use different types of the vocoder. One of the most popular vocoder is Street. Recently, since 2016, after the WaveNet appears, so there are a lot of variation of neural vocoders, which is to generate the waveform directly from the user neural network from the acoustic features. So actually, the paradigm has shifted in TTS after WaveNet appears in 2016. WaveNet changed the mindset to do the waveform reconstruction. Before it used signal processing or use waveform concatenation, but WaveNet is to use a single neural network, take the acoustic feature or even linguistic features to directly predict the audio samples, predict them sample by sample, and treat each sample as a category. Is very similar to the language model idea. So after the paradigm shift, actually, we can see from the last maybe 3 or 5 research challenges, you can see that in 2016, that is before WaveNet comes out, the mode score, the highest mode score is not close to the natural. System A is a natural recording. The best system here is the system L. The system L, you can see the media value is 4. For the natural, the media value is 5. 5 is the highest. But in 2019 is a very challenging task. 2019 is not using the studio recording. It's using some internet data to do the TTS synthesis. You can see system A is still the natural recording. System M is the best system. You can see for the media score, actually it's the same as the natural recording. Actually, you can see there are 3 systems. Their media mode score is 5. So it means the deep learning techniques has advanced the speech synthesis a lot. Also, you can see here, in 2016, most of the systems, their mode score is under 3. But in 2019, you can see half of them, they have a higher mode score than 3. So that's a good news. So because there is a technology change, so let's get a comparison between the best systems of the 2 years from the 2 years Blizzard challenge. First, for the text processing part, actually for the feature representations, it doesn't change much. It's 2019 and 2016. They use basically similar feature representations in the text processing. Maybe some underlying model for the G2P changed, but from the feature perspective, they did not change much. For the regression is in 2019, they start to use some more advanced techniques, for example, encoder-decoder. In 2016, most of only one team, the best team, they are using a recurrent network. For the waveform generator, there is a big change. In 2016, the best 3 systems are all using unit selection. And in 2019, the best 3 systems all use neural vocoder. So there is a big change in the regression and the waveform generator part. Do you have any questions for now? Okay, let's move on. Let me play you some samples. The samples are from the Blizzard Challenge 2019. It's a Mandarin corpus, but you can listen to the audio quality. I will play the ground truth. The ground truth, if you are doing speech recognition, you see the audio quality is great. But if you are doing TTS, you will say, oh, the quality is terrible. Let's play ground truth.
姜子牙辅佐武王伐纣，建立了周朝，是齐国的缔造者。周文王轻商，武王克纣的首席智囊，最高军事统帅，与西周的开国元勋。
This is the ground truth audio. There's some channel noise, a little bit background noise. This is the best system. You can listen to the audio quality and also the prosody.
姜子牙辅佐武王伐纣，建立了周朝，是齐国的缔造者。周文王轻商，武王克纣的首席智囊，最高军事统帅，与西周的开国元勋，齐文法的创始人，一是。
Another system.
姜子牙辅佐武王伐纣，建立了周朝，是齐国的缔造者。周文王轻商，武王克纣的首席智囊，最高军事统帅与西周的开国元勋。齐文化。
So for the audio quality is very close to the natural recording, and so for the prosody is also not as close as the audio quality, but is getting much better. Yeah, because the technology has advanced a lot, you may think, okay, if we already advanced a lot, what we can do? Is there any artifacts we can use when we want to detect the voice cloning spoofings? Actually, there are a lot of artifacts in each module. For example, in the text processing, even we know we have a very high accuracy in G2P and text normalization, but I would say in the real production, 90% of the error, 90% of the bug are coming from text processing. For example, if we use the English TTS system to pronounce my name, it will fail. So that's a problem of the G2P. For the text normalization, it's also not perfect. For example, the numbers, how to normalize the numbers, especially for different contexts. For the prosodic feature prediction is also not perfect. For example, the tone, for the Chinese tone, even it can be maybe 99% accurate, but for some contexts, it still can predict the wrong tones, and also the pausing. For the regression, it's doing great, but still some artifacts. For example, when we do the regression, we are trying to model the uncertainties for the unseen text. So we have to do some averaging. So this averaging will introduce some smoothing effects. I will show you a figure later. Also, there are the statistical model accuracies not that great as well. For example, sometimes you can hear some high-pitched noise. Sometimes it can feel a kind of the voicing and unvoicing prediction error. It will also introduce some errors. In the waveform generator, I believe is when we use a mirror spectrogram, when we use some features, we are still really on the short-time Fourier transform. So for the short-time Fourier transform, there is a problem is a constant frequency and the time resolution. This is different from human's perception. So there's another very interesting finding by the in the spoofing challenge is they found the silence can be used. Silence can be a very good feature to detect the spoofed speech. The reason is that when we use silence in the real production, for example, unit selection, usually we repeat the same silence pattern. So if we repeat the same silence pattern, when we concatenate the silence with any context, there should be artifacts. Another one, sometimes when we train the neural vocoder, we also do some special treatment for the silence. So this can also introduce some artifacts. So all these kind of artifacts can be used to detect the deepfake audio. Let's look at the short-time Fourier transform, the artifacts. So in the short-time Fourier transform, we use a fixed window length. I think we always, when we talk about the speech processing, maybe when we extract feature, we will say, oh, what's your window size? What's the frame shift? So when we talk about this, it means we are using a fixed window length. We are using the frequency and the time resolution, they are also linearly distributed, so which is different from the human perception. So these features, this artifact has been used to design other features to detect the spoofed speech. Another artifact is smoothing. For example, here in the left spectrogram, when we use a compact representation of the spectrogram, when we reconstruct it, it already lost some details. You can see here, especially for the high frequency part. At the time domain, because we are doing the statistical averaging and also the long-term time dependency is not that great, you can see for time domain, it also has the smoothing effect. Do you have any questions until now? Okay, let's move on.
Hey, sorry, I actually have a question.
Yeah.
I'm wondering, are the artifacts independent per component in these three components you mentioned? Is it fine to treat them separately, or are there cases when, say, something happens in the text processing step and it doesn't match well with the later steps, and that kind of mismatch is causing an artifact?
I think for some of them, most of them are independent. For example, in the pronunciation prediction, if there is a wrong pronunciation, prediction is very hard to correct it in the following modules. So for the smoothing is a kind of also independent of other modules. I think most of them are kind of independent.
Okay, I see. Thanks.
I also have a question about the smoothing effect. So is smoothing effect still a problem for GAN-based approaches such as waveGAN or mailGAN?
I think here is the waveGAN, mailGAN is more like the waveform generator. I think here is more like the, for example, if we listen to the prosody is kind of in the time domain is still not perfect yet.
Okay, thanks.
Okay, let's move on to the voice conversion. Actually, voice conversion is very similar to the text-to-speech synthesis. It can also have the three modules. For the regression part, is similar to speech synthesis. For the waveform reconstruction part, is also similar to that in TTS. Only major difference is first the analysis, how to in voice conversion is take the speech as input. In TTS is takes text as input. So what kind of features can be used for the feature extraction part? We can see what's the difference between the two speakers' voice from the feature representations. For example, here, the first column is the speech representation of one speaker's speech. This is a speech representation of another speaker. They speak the same context. What we can see is here, the duration is different, right? For the same R, they have a different duration. For the spectrogram, they also be different. You can see the energy, they are quite different. For the pitch, you can see the second speaker has a much higher pitch. The first one is have a much lower pitch. Yeah, for the energy is also different. So for this kind of difference, that is what we want to convert. We want to match the target speaker. In the regression is before the encoder decoder, most of the regression is doing the frame by frame mapping. The frame by frame mapping can be a linear regression, can also be a nonlinear regression. There are some models not using neural network, for example, non-negative matrix factorization (GMM). Yeah, they are not using neural networks. For the neural networks, they can use feed-forward neural network and can be some recurrent network like RSTM. For the encoder decoder, if we want to do the sequence-to-sequence mapping, we want to match the prosody, because when we do the frame-by-frame mapping, we cannot convert the source speaker's prosody to match the target speaker's prosody, because prosody is a long-term need to have a long-term dependency. So in the encoder decoder, it is possible to do that. For the encoder decoder is very similar to what we have done in the TTS. So the encoder here is instead of encode a sequence of letters or characters, it encodes a sequence of speech representations to get some hidden state. Then we use a decoder with attention to decode the hidden state into a sequence of target speech. We expect this to match the target speaker's speech. So with this sequence to sequence, it is possible to change the porosity. So yeah, for the synthesis to reconstruct the waveform is very similar to what we have seen in the TTS. Basically, they share the same. The only difference is voice conversion usually does not use unit selection because voice conversion is not using too much training data. For the unit selection, it requires a larger data set. Because of the technology change, actually the voice conversion, the quality and the similarity also improved a lot. Here is a summary of all the submissions in voice conversion 2016. That is before WaveNet. So you can see here the best system, the similarity is still under 80. Have a large gap between the target. So for the quality, the best systems also have a very large gap between the natural recordings. In this year's voice conversion challenge, because of the new technology, you can see here for the most score, half of them are much better, have a higher score than 3.5. You can see the best systems, they are very close to the target in terms of quality. In terms of similarity, half of them are much higher than 80. 80 is the highest in the voice conversion challenge in 2016. So you can see here the T10, T22, T27, they are almost the same as the target. That's the good news. Yeah. That's a good news for the quality of the voice conversion, but this is bad news if they use this technique to create some fake data for the DC information. So
I have a question. Could you go back to the slide? Could you describe what you mean by the speaker similarity?
Oh, speaker similarity is a kind of we will ask the listener to see whether the sample sounds like the target.
Okay, so it's subjective.
100% means all the listeners say, oh, all the samples are the same as target speaker.
Okay, thanks.
So here is a summary of what kind of techniques has been used in the best system in the 2016 and 2020. For the acoustic feature representation, you can see in 2016 is still using some human-defined features, for example, the capture features, F0s, but the best two systems in 2020, they use ASR acoustic models to extract the phonetic posterogram. Use this as a feature to the voice conversion regression model. For the regression, also the model change. You can see the best two systems in 2016 is using a very simple model, the GMM and the feed-forward neural network. In this year, the best system is using RSM or encoder-decoder. Also a big change in the waveform reconstructor. The best system in 2016 is using STREET, is a signal processing based vocoder. But this year is the best two systems all use WaveNet. They use a neural network to generate the waveform. Let me play some samples. Here is a source. I will play source, target, and converted. The converted is the baseline system in 2020.
The problems I mentioned are not insurmountable.
Target.
Moroccan agriculture enjoys special treatment when exporting to Europe.
Converted.
In reality, the European Parliament is practicing delay tactics.
Another one, another main one.
The problems I mentioned are not insurmountable.
Target.
Moroccan agriculture enjoys special treatment when exporting to Europe.
Converted.
In reality, the European Parliament is practicing delay tactics.
Yeah, for the artifacts, it's very similar to that in TTS. The only difference is in TTS there are some artifacts coming from the text processing module. So here is in the analysis part is very similar to the artifacts in the TTS. For the regression part is also the same as in the TTS. For synthesis, it's just basically the same. So if we design a detector to detect the best voice conversion or the TTS fake audio, so it is possible they can share the same detectors. To summarize what we have talked so far is for the TTS and the voice conversion, the two techniques have been advanced a lot in the past few years because of the development of the deep learning models. So the state-of-the-art voice generation techniques can produce speech that is very close to the natural speech. But even the techniques can produce high-quality speech, but there are still a weakness in these techniques. These weaknesses can be used to design the deepfake detections. Do you have any questions? Next module, we will talk about how do we detect the deepfake audios.
Zhizheng, I have a question. This is Corey Miller. Could you talk a little bit about style transfer? I have the impression that's a little bit like voice conversion in that you could take certain components of a voice, maybe the gender, the accent, or the personality. So I'm just curious what you think about that.
Yeah, style transfer is a kind of, we can say used in the TTS. I think currently mostly used in the TTS. For example, if you have a few recording of your voice with some specific styles, actually we can use some style encoder to get a kind of representation of your style. It's very similar to get the speaker embeddings. Right, we can use that the style embedding as the input to the TTS to reconstruct the speech speaking in that style. Did I answer your question?
Yes, thank you.
Can I ask a question? Right. So I actually would like to know about the amount of data, parallel data, that perspective, because everything is now based on the data-driven approach. So, TTS as well, but the VC voice conversion, usually have a kind of serious, the sparse parallel data issues.
Mm-hmm. Yeah, I think it is. You can see, look at these numbers. Look at these best systems. If we use a phonetic post-series as the input, and use a target speaker as the output. Actually, in this case, we don't need any parallel data. Yeah. So if we do not use parallel data, actually we can pre-train a model on any data what we have, and then tune for that target speaker.
I see. That part is also kind of already solved or can be solved.
I think it's already good, but I think it's not always perfect, right?
Yeah. But very interesting. Okay, thank you.
I have a question about effectiveness. So, so without any deepfake detectors, what do you think is more easier to spoof? Is it the text-to-speech version or is it the voice conversion version?
Maybe we can leave this question answer in the next part. Yeah. I will show you some spoofing detection result. I will answer this question later. Is it okay?
Sounds good.
Yeah. Okay, here let's come to the how to detect the deepfake audios. So Actually, recently there are many deepfake detection in the video or the photos. Actually, in the audio, they start to look at this problem very early. I start to in my PhD, I originally working on voice conversion, but because I know too many speaker recognition guys, so after we talk, why don't we do some experiment to spoof the speaker verification system? So we did some work, found it is quite interesting. So in the 2012, we did the first large study on the NIST evaluation data. We found, it's really a problem. It can spoof at that time the state-of-the-art systems and a very large margin. So in 2017, there is a special session at the inner speech. So at that time is to start to look at the spoofing problem. At 2015, we created a very large data set based on the VCTK. VCTK data set also used in this last year's spoofing challenge. That data set have hundreds of speakers and about 10 spoofing techniques to generate the corpus. So we use that corpus to organize the first voice conversion challenge in 2015. In 2017, there is a playback because in the voice biometric system, we need to play the audio in front of the microphone. So last year, they come back to revisit to detect the synthetic sample and also at the same time to have another task to detect the playback. So in the first challenge, in the ASVspoof 2015, the task is very simple. Even we say it's automatic speaker verification challenge, but has nothing to do with the speaker verification. It only asks the participant to build a simple classifier. The classifier is to classify whether the audio is a bona fide sample, is a real sample, or a synthetic sample. So that's a very simple task. So there are, let me play you some samples. In this sample, this one is I first play the real recordings, the real sample.
Why do you want to come to Edinburgh?
Let me play one, maybe two synthetic. One is using the TTS.
It's nice to hear.
Is another voice conversion using the open source.
It's nice to hear.
Let me play the S10. You remember S10. We will talk about S10 a lot in this in the following maybe few slides. S10 is a unit selection.
It's nice to hear.
Perceptually, the quality is very bad. So, but in the real detection is very challenging. So here is the result from all the submissions. For the known attacks means we already released some training data for this kind of attacks. For the unknown attacks means the participant only see them in the evaluation data. They never see it in the training data. So the last column is the average score of the equal rate. I think equal rate, I assume everyone knows equal rate. So here you can see here is for the known attacks, the error rate is pretty low, but for the unknown attacks, the average the equal rate is much higher. Even for the best system, they have the system A. The equal rate on the unknown attacks is 5 times higher than that on the known attacks. That is not good news because it means it cannot generalize very well for the detectors. Let's look into further. Here is the most successful countermeasures in the ASVspoof 2015 is using this feature. If you are interested, you can read their paper. This specific feature is to take some feature is the auditory transform, and also take some feature. In this feature, also include some face-related features. I want to share with you the result here is for the no attacks. This one works perfect. Oh, by the way, in this system, they use a very simple classifier. It's a very simple GMM classifier. But for the unknown attacks, it works okay for S6 to S9. But there is one is S10. It's very difficult to detect. S10 is a unit selection. From when we listen to it, the quality is pretty bad because when we train this system, we only use 40 utterances to train the model. It's not enough data to get a very high quality unit selection.
Zhizheng, you have 5 minutes essentially.
Okay, yeah. Should be maybe 2-3 minutes delay. Yeah, let's move on. Okay. Another feature after the evaluation, there is another successful feature. It's called the constant Q feature. This feature is already, actually you can see in the comparison to the short-term Fourier transform. In short-term Fourier transform, the time and the frequency resolution, they are also constant. But in constant Q is already the opposite. It's the time and the frequency resolution, they are variables. So this feature, because it addresses finds the weakness in the short-term Fourier transform, it works perfect to detect the attacks. So you can look at this number. In the S10, the best system in the challenge is this one, is the 8% equal error rate. When we use this feature, we get only 1% of the equal error rate feature, equal error rate. So it means if we know the weak point in the TTI system or voice communication system, we can define some features to detect that. I want to mention that in this feature, it's also use a very simple classifier. It's a GMM classifier. So for the ASVspoof 2017 is to detect the playback. So we will not go through this here. If you are interested, you can read the review paper and find the paper in that special session. 2019 there are 2 tasks. One task is a logical access task. It's the same as we did in the 2015. Another one is a physical access task. It's assuming we need to play back the audio in front of a microphone. So we will only talk about this logical access task in here. If you are interested, you can read their summary paper and the papers in that special session. In 2019, there are large contributors to the dataset, including Google, Appletech, from the academia, also from the industry, also from a lot of universities. They contributed to the dataset. Yeah, here's a summary of the system. I play you 2 or 3 samples. Let me play you the one of the interest is A10. A10.
We did not compete with any other local format.
And A11.
We did not compete with any other local format.
I want to mention is for A10 and A11, the text processing and the regression model, they are the same. The only difference is in the waveform generator. A10 is using the WaveRN, is a neural vocoder. The A11 is using a signal processing vocoder. Okay, let's move on. Here is a visualization of the data set. This is A1 to this A19. They are the different spoofing techniques. So here the visualization is we compress each utterance into an X vector and use a TSNE visualization. You can see here the A4, A10, A11, and A16. They all have they have some overlap with real speech. So the real speech is a gray dots, So here, one interesting is A10 and A11. The text processing and the regression model, they are the same, but they are only using different vocoders. So, but in this space, they are very close. It makes sense. For the A4, A16, and A4, they also have the overlap with real data because they are using as a raw audio and do the concatenation. Okay, this is an important slide. This is the task this is the ASVspoof result on the logic access task. The baseline of the system is 2.5%. So if we use spoofed data, you can see the equal error rate increased a lot. The highest, for example, the A14 increased the equal error rate from 2.5 to 64. It's like a random guess. For the detector performance, this is a median result of all the systems. You can see here for the A10, it's much harder to detect. Yeah, A10 and A11, the only difference is the vocoder. For the A13, it's also much harder, and same for the A17. Let me play you 3 samples. First is A10. You listen to the quality. A10.
We did not compete with any other local farmer.
A13.
We did not compete with any other local farmer.
A17.
Where are they for?
Yeah. So the audio quality of the A13 and A17 is it's quite bad, but it's very hard for the detector to detect. I think 2 more minutes. Yeah. Okay. Here is the best system in the challenge. For the feature, from the feature engineering point of view, it's nothing special. It's very similar to the features used on the ASVspoof 2015 data. One thing they found useful is the silence. As we mentioned earlier, there are some artifacts in silence in the TPS system. The classifier is using much better classifier, is using convolution network instead of the very simple GMM in 2015. Even for the best system, we can see the equal error rate is still not generalized very well. For some system, for example, A7, A8, A9, they got a very low error rate, but for A17, A13, they get a much higher equal error rate. It means even the best system cannot generalize very well on different attacks. Another finding is you can see that as we have listened, the A13 and A17, the quality is very bad, but it's very hard for the detectors to detect. It's a good news, it's also a bad news. The good news is if they use A17 to create a disinformation, the ordinary people can know, oh, it's a fake one. But the bad news is if we use it for the voice biometric system, it's very easy to spoof the system because the humans are not listening to it. This is a comparison of the features. For the feature is very similar, all use the capture related features, but for the model is using more advanced model in the latest challenge. Okay, here's we want to see we from the challenge we see some there are no correlation between the detection and the audio quality. Yeah, recently there is a study to learn whether there are any correlation on the voice conversion challenge 2020 data set. So they found that actually the correlation is complete no correlation. You can see the correlation value is 0. 1 means that is a perfect correlation. Even -1 means a perfect correlation, but 0 is completely no correlation. So here the summary is for the state-of-the-art detectors can detect most of the audio deepfakes, but this kind of detector cannot generalize very well on some unseen audio deepfakes. Also, a good news or bad news is there's no correlation between the audio quality and the detection for the error rate. So what's next? Currently, from what we can see in the literature, all of the fake audio detection is focusing on the voice biometric application. But from my point of view, there's a more serious problem is disinformation, because disinformation can do things differently. For example, recently there are many TTS techniques. They can allow you to only generate to modify a few words in the utterance, and also very natural. There's no glitches. So for this kind of detection, because the entire utterance, maybe only 10% of the words are fake, and 90% of the words are real. So how do you decide is the real or the fake? So I think this is a very challenging task, especially if we use this to use a disinformation, right? Another challenging task, as when I play the audio to you, is when they mix the fake audio with some noise or background music. So it also makes the detector fail. Okay, that's it. Thank you. Any questions? Do we have time to take questions?
Yeah, let's have a question or two.
Yeah.
Thanks for your talk. Very interesting.
Thank you.
Jason?
Yeah, hey, I have a really high-level question. Thanks, first of all, for the talk. Like a lot of people, I'm really concerned about this problem, and I don't know how to solve it. One reason I've thought it would be hard is because anything we can use for detection could be plugged back in to make better generation. So GANs, for example, give a recipe to do that. So is there any way out where by coming up with better detectors, if we don't keep them secret, we're not just enabling people to do better imitation of people's voices?
That's a great question. Actually, I don't have an answer to that. Maybe we can take some what we have seen. For example, in 2013, we found the modulation feature can be used to detect the fake audio. But in the 2014, in the TTS, they use the modulation to improve the TTS quality. So it's a kind of arm race. Is in Chinese we call it. I don't know how to translate it in English. I can't say Chinese. If someone knows how to translate in English, please help. Is 道高一尺，魔高一丈. Is a kind of arm race between the two guys.
Arms race works. Yep.
Yeah. Yeah. Thanks for the question.
I mean, one question actually is whether hardware, whether there's some solution in hardware to make sure that devices that are recording actually sign what they've recorded, so it's a real recording. But I think there are attacks on that as well. Like they could be, instead of recording the original speaker, they're recording some device that's emitting the deepfake. So I don't really see any way out, and it scares me.
Yeah, I found there. I remember there is a paper. They use some sensors to detect whether there is a live people in front of the microphone. Maybe this can be.
That's great.
But I think for this kind of, if they can still use the deepfake to create some misinformation. For example, I say I own Shinji 1 million, but I can't say I can change it to I own Shinji $1. Right?
Okay, one more question or comment? Okay, so if not, then let's thank Zhizheng once more and see you next week, I believe.
Thank you.
Thank you.
Have a nice weekend.